All right, hi everybody. Thanks for checking in today. We're going to be looking at, as it says right above my head here, proving trig identities. Hey, we've dabbled in this a little bit. We've verified, it's another word that I use instead of proving sometimes. We've proved or verified a few identities, but today we're going to get a little bit more specific on how we go about doing that. Along with proving trig identities, there are several more identities that we're going to take a look at. We've got a bunch of them that we know already. We're going to add to that. So let's talk about the process that we use and some helpful tips as we prove trig identities. So first one, there's a couple different options. We can either work on one side of the equal sign until we get to the other. Okay, so if I'm going to show you what we're going to do here in a second, here's our first identity that we're going to prove today. I can work on one side of the equal sign. Okay, so for example, I could pick this side, work on only that side until it equals the tangent. Okay, or I could pick to work on the right side of the tangent of x and work on that until it equals this left side. So that's option one. Option two is to work on each side separately until they're the same. Okay, so I do something on this side, I do something on that side, so I'm working on them separately until they equal the same thing. Now, when I say separately, I mean we have to continue to work on them separately. What we can't do is we can't be moving things to either side of the equal sign. Okay. For example, I can't add something to the left and add it to the right to switch it. We just try to want to work just within that side. Okay. Number two, it's usually best to try the more complex or complicated side first. I think I've already mentioned that in class. It's easier to take something complicated and make it simple versus take something simple and make it complicated. Number three, you may use any previously established identities. Anything that we've talked about, you can use. Anything that we already know. So I just grabbed a little trig identity sheet here, and these are all the identities that we should already have. We've got our quotient identities for tangent, sine over cosine, and cotangent is going to be the reciprocal. We have all the reciprocal identities. We have our Pythagorean identities. I just grabbed this offline, so the second and third one may look a little different than what we wrote when we talked about them the first time, but that's okay. It's just a rearrangement. We know what functions are even and odd. We've discussed that. Our sum and difference identities, these are the first real big identities that we looked at. We've also discussed our double angle identities, half angle identities. As you can see, I've covered up some more because we got more to learn. And number four, it's helpful, I know I've mentioned this, it's helpful to rewrite as only sines and cosines. It tends to make things a little bit more clear on what our next steps could be and how we could possibly use some of these identities. So let's work on this first one together. Well, as I mentioned, it's usually easier to start with the more complex or complicated side. That's the left side here, so I'm going to work with that. Now, also looking at that, I have a tangent here. Probably my best interest to switch that to a sine over cosine might make something a little easier for me to see on what I could do. All right, so I took our tangent, I rewrote that as the quotient of sine over cosine. I put an equal sign here. Now I could just continue to write tangent of x on the right side all the way go down. It's going to be a bit redundant, so I'm not going to do that. I'm just working on that left side. I'm going to leave this equal sign here. I know that's tangent. Okay, we're going to continue that until we get tangent on the left side. Now, looking at this, okay, now it's decision time. Try to figure out what can I do to make this a little bit more simple, to simplify it. Well, I have a complex fraction. Okay, I have a fraction within inside this bigger fraction. We know methods to simplify that. So one thing I could do here is I could multiply everything by the cosine of x over the cosine of x, multiply it by that denominator. On the top, when I distribute that in, I get a sine of x, cosine of x, plus, when I distribute to this term, cosines cancel, leaving me with just the sine of x. Over. Now I'm not going to distribute this in because I'm already noticing something in the numerator that I'm going to be able to do. Okay? Look at that numerator. Okay? What can I do with that? Well, I have a sine term in each of these. I have a sine of x in that term. I have a sine of x in that term, which means I can factor that out. Why would I want to factor that out? Because it leaves me with a cosine of x plus 1. So the sum of cosine and 1. And what do I also have on the bottom? I have 1 plus the cosine of x. Now I could take a step, if you need me to rewrite that using the commutative property and just switching the order of the sum. But I think that everybody in here is well aware that the cosine of x plus 1 is 1 plus the cosine of x. Those cancel. Okay. Leaving me with the sine of x over the cosine of x. Well, what are we trying to get this to equal again? Okay. I said I was leaving this blank just to save myself some redundancy in writing. Okay, but we're trying to show that this left side is equal to the tangent. And look what we have here. We've got sine over cosine, which is the tangent. So we have the tangent of x equals, on this entire side, that was the tangent of x. Does the tangent of x equal the tangent of x? Yes, it does. We just proved that identity. Awesome. Worked with that left side, rewrote tangent to sine over cosine, multiplied by that denominator, did a little factoring, a little canceling out. Got it. All right, let's take a look at this other one. Next up, we've got proving 1 plus the sine of 2x is equal to the sine of x plus the cosine of x squared. All right. Do I want to work on one side, the other side, work on both sides separately? What do I want to do here? I think I'll continue just to work on one side. Which side's more complicated? This is a little complicated because we're taking the sine of 2x, not just x. You could make an argument that this is a little more complicated because we're squaring this sum. Really, I think you could start this one on either side and be able to successfully show that it's equal to the other without too many steps. I'm going to work on the right side on this one. I have the sine of x plus the cosine of x squared. Okay, now working and simplifying that, I know if I'm going to square this, I should FOIL. So this is the sine of x plus cosine of x times the sine of x plus the cosine of x. Okay, and let's FOIL this out. I get a sine of x squared. Outside, sine of x, cosine of x. Inside, cosine of x, sine of x. That's the same thing. That's really 2 sine of x, cosine of x, plus cosine of x times cosine of x. We have a cosine of x squared. All right. How was that helpful? What do you see there? I see a sine squared of x plus cosine squared of x. If it's helpful for you to see this, I'm going to write this in a different order, changing the order of my sum. Oh, I lost a squared. There it is. There we go. I have the sine squared of x plus the cosine squared of x. What do we know about that? It's one of our biggest identities. That's a Pythagorean identity. Okay, let's go back to the sheet I grabbed. Where can I see it? Right there. The sine squared of theta plus the cosine squared of theta equals 1. Okay, we know that that's a 1. 1 plus 2 sine of x cosine of x. Look at this left side where we're trying to get again. We've got 1 plus. We've got 1 plus. That means this is what I need. This is what I have. I've already got the 1 plus. Sine of 2x, 2 sine of x cosine of x. That looks a little familiar. Sine of 2x, that's a double angle, isn't it? The sine of 2 theta equals 2 sine of theta cosine of theta. What's the sine of 2x equal to? 2 sine x cosine x. Hey, this is really 1 plus the sine of 2x. Got it. Now, that might make you see how we could work with the left side instead. And I'm guessing your curiosity, okay, is piqued enough here that we should probably just look at what would this look like if we worked on the left side instead. So I'm going to duplicate this page. Where is it? There it is. Yep, all right, we've got 2 of them. And let's delete this. Let's just work on the left side. 1 plus the sine of 2x. Well, we know that's 1 plus. What's the sine of 2x again? 2 sine of x cosine of x. Now I want to get this to equal the sine of x plus the cosine of x squared. Well, and this is probably why I picked this the first time to go the other way. What I would need to do now, realizing that I have the sine of x plus the cosine of x squared, is to look at this 1 and realize 1 is the sine squared of x plus the cosine squared of x. Okay, substituting that in using the Pythagorean identity, then realize, okay, if I rewrite it like this, it's a little bit easier to see that this is something that I can factor. That is the factoring of, or the foiling of, the sine of x plus the cosine of x squared. So we could work on it that way. That way might not be as obvious. Doing it this way, I think, made it a little bit easier. But we had to realize that we had to replace the 1 with the sine squared of x plus the cosine squared of x. Again, it's a little bit easier to take something more complicated like this and simplify it versus taking something that's a little bit more simple and making it complicated. All right, so there's a couple examples of how we prove identities. Remember those guidelines that I have there for you. What I now want to do is to look and see if there's any more identities that we can develop. Okay. So we have formulas for rewriting sums. Let me go back to this sheet here. Our sum formulas look like this, right? The sine of theta plus phi, fo fum. I don't know, it's early in the morning. I'm blanking on that one, which of those names it is. we wrote it as the sine of x plus y. So we can take the sine of a sum and know what that's equal to. Can we write a formula or identity for rewriting a product? In other words, can I take some sort of product, maybe something like this, and rewrite it somehow? Well, let's use our sum formulas or sum identities. The sine of x plus y. Sine, cosine, plus cosine, sine. Sine, cosine, plus cosine, sine. And our difference one, let's look at our difference. Sine, well, it's the same thing except it's a minus, isn't it? There's a minus on the bottom there. There's a minus on the bottom there. That's going to be the same thing. So this would be sine of x cosine of y minus cosine of x sine of y. Time to be clever. What would happen if I added those together? What would I get? Well, on the left side, I would have the sine of x plus y plus the sine of x minus y. What do I have on the right side? Notice those terms are the same. I would have 2 sine of x cosine of y. Now, when I add those together, those are the same. Those cancel. Now, take a look at this. Our goal is to write a formula for rewriting products. Notice we have 2 times the product of the sine of x cosine of y. So what I could do with this is I could take each of these sides and divide them by 2. This gives me the product of the sine of x times the cosine of y equals this, the sine of x plus y plus the sine of x minus y divided by 2. Okay. That is this first identity right here. The sine of x cosine of y is equal to 1/2. Where's the 1/2 coming from? It's this dividing by 2, the sine of x plus y plus the sine of x minus y. That's our first product to sum identity. Okay. And you can see that we could develop 3 others as well. All right, I'm going to move on. If you needed to pause and finish writing, go ahead and do that. Okay. So let's put this into practice. Okay. Let's rewrite this as a sum. We have the sine of 2x times the sine of 8x. Okay. That's a product. I want to rewrite it as a sum. Now, I know right now we're doing that just to do it, but there's going to be times later on as we're working through something where it will be our advantage to rewrite something as a sum instead of a product. Now, what is this the product of? 2 sine functions. Here's the product of 2 sine functions. So we're going to be following this. Okay. So this is going to equal 1/2 times the cosine of x minus y. Our x is the angle of our first sine. Our y is the angle of our second sine. Okay. And we're going to take the difference of those. What's the angle of our first sine on this one? 2x minus, what's the angle for our second sine? The 8x. Minus the cosine of the sum of those. 2x plus 8x. So this is 1/2 times the cosine of, negative 6x minus the cosine of 10x. So this is 1/2. I'm going to distribute that 1/2. I don't like those big parentheses. Cosine of negative 6x minus 1/2 times the cosine of 10x. Now, taking a look at this, that's pretty good. We kind of accomplished what we needed to accomplish. We rewrote this product as a sum. One more thing that I would do here, just looking at it, I don't know, just not a fan of taking the cosine of negative angles. What do we know about the cosine of negative 6x? What do we know about cosine? Is cosine even? Is it cosine odd? Well, if you need to look back at a sheet here, even odd identities, the cosine of negative theta equals the cosine of theta. If I take the cosine of one angle versus the cosine of the opposite of it, those are the same. So I might as well just clean this up a little bit more by saying this is 1/2 times the cosine of 6x minus 1/2 times the cosine of 10x. Not too bad, huh? So, sum to product identities. Now, we can use the product to sum identities to write sum to product identities. Yeah, there's a lot of identities, a lot of things that we can do. So, I want to write an identity, and I have a misspelling there, to change a sum into a product. To change a sum into a product. Well, this should look familiar. We just talked about this one. This is the one that we developed a few minutes ago. Notice here I have a sum of two sine functions here. So I'm going to use this to figure out what that's equal to, the sum of two sines. I'm going to multiply each side by 2. Let's stick in the blue here. 2 sine of x cosine of y equals the sine of x plus y plus the sine of x minus y. Now, when I say I want the sum of two trig functions here, I don't want the sum of two trig functions that have angle additions inside of it. What I really want is the sine of some angle plus the sine of some angle equals something, if that makes sense. So what I want to do here is I want to replace this with just one angle. And because I already have x's and y's in here, I'm going to just choose a different letter, and I'm actually going to go Greek on this. I'm just going to call that, let's just call that alpha. And I'm going to call this angle, let's go beta. If I have the sine of alpha plus the sine of beta, so I have the sum of the sines of two different angles, what does that equal to? Well, we know this equals to 2 sine of x cosine of y. Well, this now needs to have alphas and betas in it instead. We can't be sitting here and magically changing this alpha to an x or this beta to a y or something like that. We have to know, how do we get these angles from those angles? I'm going to leave that as a question mark for right now. We need to figure that out. What's going to help us figure that out is realizing that alpha equals x plus y and that beta equals x minus y. So, can I solve this for x and figure out what x is in terms of alpha and beta and what is y in terms of alpha and beta? All right, well, I'm going to have to do some solving here. would you agree that alpha minus y is equal to x? Now, that's not enough because this still has a y in it. Okay, we want only alphas and betas over here now. So how could I help myself out here? Well, I don't want this y in it. I can figure out what y is equal to over here. Y is equal to x minus beta. So I believe I could substitute x minus beta in for this y. Alpha minus x minus beta is equal to x. So in other words, alpha minus x minus beta equals x. Can I solve this for x? Let's add x on both sides. Alpha minus beta equals 2x. Dividing by 2 then, alpha minus beta over 2 equals x. So coming back up here, this x, that angle, comes from taking alpha minus beta and dividing it by 2. Now we need to figure out what y is in terms of alpha and beta. Well, y is equal to x minus beta. What's x equal to? Alpha minus y. So we're going to go y equals alpha minus y minus beta. So 2y equals alpha minus beta. I think we can see where this is going. Y equals alpha minus beta over 2. So what do we have? Let's go back up to this step. We have 2. Let's go back to blue here. 2 times the sine of alpha minus beta over 2 cosine of y, which is alpha minus beta over 2, equals the sine of alpha plus the sine of beta. All right. Now, just to stick consistent with what we've been writing in our notes, okay, we're going to change these back to x's and y's. That was the sine of alpha plus beta, so that's going to be this one, and I see that I had a mistake. I had a feeling this was happening somewhere in here. Oh, here we go. Live on television, right? Here we go, making a mistake. I know one of these is supposed to be a plus and one is supposed to be a minus. Where did I go wrong? Oh, right here. There it is. Okay. Forgot to distribute my negative. That was supposed to be a plus. Okay. I'll have to go back and watch the video even if I said I was distributing the negative and I didn't actually do it. We'll find out that was supposed to be a plus. That's a plus. That's a plus. That's a plus. There we go. All right. So there's our first sum to product identity. The sine of x plus the sine of y, so the sum of the sine of two different angles is equal to 2 sine of x plus y over 2 cosine of x minus y over 2, and we can have 3 more of those identities that we could develop in similar fashion. So again, if you need to pause that to finish writing that up, you're welcome to do that. Okay, I want to finish just looking at this. Rewrite as a product. I have the sine or cosine of 3x plus the cosine of 5x. I want to rewrite that as a product. Hey, this is cosine plus cosine. We're taking a look at this second one. The cosine plus cosine equals 2 cosine x plus y over 2. What's my x? What's my y? Those are those two angles. That's 3x plus 5x over 2. Cosine of x minus y over 2. Cosine of 3x minus 5x over 2. So this is 2 cosine. 3x plus 5x is 8x divided by 2. That's a 4x. Cosine 3x minus 5x is negative 2x divided by 2. Negative 2x divided by 2 is negative x. I don't like the way that looks. I'll put parentheses there. I might as well put parentheses here. Now, just like on that other one that we did a few minutes ago, we know the cosine of negative x is equal to the cosine of x. Good. You know what? We haven't done this yet. Might as well do it at least once. Let's graph this. Let's just see that everything matches up. Okay, we had the cosine of 3x plus the cosine of 5x. And we get this pretty graph here. Okay. We know the cosine of 3x would be taking our normal cosine graph and doing what? Horizontally compressing it down. The cosine of 5x would be the same thing. We're horizontally compressing it down, but even more so, we're shortening that period. So we end up with the cosine of two different we end up with graphs of cosines with different periods, and when we add those together, okay, we get this. Let's see, does that equal 2 times the cosine of 4x cosine of x? 2 cosine 4x cosine of x. Look at that. Very nice. Okay. So, took a look at a lot today. Might as well go back and do the grand reveal here on this sheet. Okay. Oh, well, we've kind of talked about that one. We've got to talk about that just a little bit more. But what we looked at today, there's our sum to product, and there's our product to sum. Okay. So, good luck today and in the rest of your practicing proving trig identities. We now have a few more tools in sum to product and product to sum. Overall, pretty good day. Thanks for tuning in.